glad to see so many of you here. I had no idea who I was going to be talking to today. My background is British, as you can probably tell. I did a first degree in physics, and then I did a PhD in meteorology in London back in the 60s, if you can remember that back that far. And I came to this country as a postdoc in 1970 and worked for 7 or 8 years on an academic track at Colorado State University. And then I decided I wasn't going to spend my rest of my life in an academic institution, and I essentially opted out of the system, moved to Vermont. I built a house in the hills of West Paulet, which is about 70 miles, 80 miles south of here, with photovoltaic electricity. In the 70s, I ran my first IBM PCs on photovoltaic electricity, and I lived there for a decade or so, and until, as things will happen, I got married, had children, and it was you couldn't get there in winter. But I've spent 30 years funded by the National Science Foundation and NASA doing research on weather and climate problems. And in the last 5 years, I would say, I've spent a lot of time around Vermont trying to explain climate change to whoever wants to know. Schools, kindergarten through high school, university groups, the legislature when they ask, business groups, citizens groups, library groups, whatever. And this talk is kind of a synthesis. There is some science here, but this is a very, very large topic, as you can well imagine, and I've got 50 minutes or 55 minutes or so to talk about it. I'm going to spend as much time on the problems that we have with our value systems and the climate system and the Earth system in general, our social values, our political values. I'm even going to touch on our religious values because I gave a similar, somewhat different talk at the Congregational Church in Burlington last week. I'm going to talk a little bit about the climate system and the water cycle and try and explain it in terms of the climate through the seasons that you all understand very well. And background of all this, as you can imagine, is all the choices, the responsibilities that are there, whether we like it or not. And I expect we'll have some time for discussion. Now, the Earth is a huge challenge for us, as I'm sure you all know. And it's a challenge because we have to integrate all that we know across all our disciplines of knowledge and all our thought and social systems. And we're faced with a system that there is enormous interconnectedness, a lot of which we don't understand, between life and climate on Earth. Now, I was trained as a scientist. Now, I had many other trainings along the way, but the frame at which I view the world is, in large part, a scientific frame, even though I pushed it to a lot of limits. And the advantages and what I call here the strengths of science is that it has a certain integrity, it deals with things with honesty, and it deals with everything we can communicate with each other. That is, all the things I'm going to talk about to you today, I can explain to you. They're not in themselves mystical or anything like that. We have a society now, though, where, particularly in the climate area, there's a lot of attack now on climate science as a field. And we have a society where disinformation, manipulation, trying to represent points of view, essentially deception, is rampant. And we have a society in which understanding of the big picture issues is also very limited. So science is of some value to us in a society which I've described here as lost in ignorance and deceit. But at the other end, science has rather severe limits because, the opposite of up there, we tend to be only able to deal well with the things that are tangible, measurable, and communicable. And there's a lot of human experience that's not in that category. And there's a lot of the natural living world and its complexity, which is very difficult for us to deal with, mostly because we understand it poorly. Now, I want to draw a distinction which E.F. Schumacher made 20 years ago, probably. He made the distinction between the man-made world, now we would say the human-made world, and what he called the creative world. And I'm just going to call it the natural world for this purpose. And this is the world of all our technology. Everything that we as human beings made, we understand it. You may not understand it, but you could, in principle, pick up the phone and talk to someone who built it, designed it, and understands it. And largely that world that we made is more or less predictable. Every now and then an engineer makes some mistake and a bridge falls down, for example, or a nuclear power plant leaks. But the natural world is not really in that same category at all. It's much more complex, and most of the important parts of it are biologically coupled. We are still, despite staggering developments in the last few decades, struggling to understand, and we're way away from being able to predict most of the natural Earth system. And to that extent, a lot of what happens in the long term with climate change is unpredictable. The other general remark I'm going to make here, and I've got a number of these slides, you'll have to bear with me, is that whether we use religious, social, or technical language, humanity is an integral part of the Earth system. And the maintenance of our civilization depends upon the stability of the Earth system. So we do not have the freedom to do whatever we wish, whatever our economic or theological values, doctrines are. And you may think, well, that's obvious. You may think that's a horrible thing to think. But if you think of yourself living here in America, where individual freedoms, for example, are enshrined in the Constitution, but absolutely nothing is said about the Earth's ecosystem in the Constitution, typically we assign rights to ourselves as individuals, ourselves as a society, and we have no value system for dealing with the Earth system. We think we have freedom, basically, to do whatever we want. And that is used over and over again in the political forum. Unfortunately for us, our numbers have grown so great, our impact has grown so great, that what I'm going to call human-centered arrogance here, the response of the Earth system to our arrogance this century will be so large that we will rethink our doctrine. And the sooner we rethink it consciously, the better off we're going to be. Another way of perspective on this is to just look back on the last few centuries. And I've used the slogan, powerful but foolish. A few centuries ago, we and our civilized thinkers thought of ourselves basically at the mercy of the elements. We didn't have a lot of technological power. We were still using wood and charcoal to give us heat, for example. But in just 2 centuries, we've got enormous technological power. And that, of course, has given us a lot of freedom. It's simple freedoms, freedom to move around, freedom to control, the temperature, humidity, and CO2 in this room. But with that has come a whole set of doctrinal beliefs, essentially arrogant beliefs, that we are now seeing are incompatible with a sustainable Earth system. And the problem, again, is either we change our view and start to manage the Earth system intelligently, or we'll be managed by disasters in the future. Now, we're moving into a little more doctrinal stuff here. Most of Western political and economic doctrine and theology was formed when humanity had a very limited understanding of its relation to Earth. Well, when our impact was small, it didn't really matter what we believed. We could have all sorts of belief systems, name them political or name them theological. But with the Industrial Revolution, powered by fossil fuels that's accelerated in the last 50 years, we are now having a global impact on the natural world. And we have to understand our relationship to it. Now, it's really our science and technology that created this situation. And we have to use them to develop more efficient societies, develop ways in which we can live within the Earth system and have less of an impact. But the Earth as a global system is now out of balance, and there's another fundamental problem. Science is essentially valueless. The way we set up and train our scientists in our society is to train them to be technicians. We train them to leave value choices to somebody else. In part, this is a result of the very long split between science and religion that goes back centuries. And you can think of that as a compromise of mutual convenience, codependency in psychological terms. Science said, okay, you leave us alone and we'll leave you alone, and we can preserve the factual integrity and honesty of what we do. And the religious world say, that's your domain, leave our domain to us. And this is true, of course, of our political society now. We're now in a strange world where increasingly, even in the political world, people think that they can manipulate reality to fit doctrine. we can change reality base. We can choose what we wish to believe in. If it doesn't fit our belief system, and this is more true now in politics probably than theology, oh, well, too bad. But the side effect of this is that no one is willing to, the side effect of this big split is that no one really was willing to accept responsibility for the Earth. The professional societies like meteorology and atmospheric science that I belong to find it very difficult to make more than very conservative statements about the impact of what we are doing to the planet, for example, in its climate system. But if no one accepts responsibility, again, we're faced with a possible collapse of the human system. And to push this to its final limit, if I was speaking to a church, I say something like this. The laws of science and the creation are not separate. They show us paths ahead for the future. There's only one world, one reality, and it's our understanding that is limited. We have to try and understand the world with all the tools we possibly have to understand in some sense what is truth. But truth, of course, is very, very complex, full of paradoxes, full of complexities, and in human life, full of tragedy and richness. But in religious jargon, it's the truth that relates us to each other and to reality and sets us free. Free, though, to face our responsibilities to the world. Now, I'm stressing this because of the attacks that we are seeing increasingly on the scientific method and science itself. Truth is very complex, particularly dealing with the Earth system, but it's critical that we make some effort. What we are dealing with now is an industrial system powered by fossil fuels, a global planetary population which is probably way above what the Earth can support, and an Earth that's out of balance in energy terms, and an Earth whose timescales are very long, meaning that everything that we've done in the last 50 years will have an impact for the rest of this century. It's much easier for our political society to try in the short term to spread uncertainty. There's doubt, there's uncertainty, things we don't know, and basically delay taking any action to face up to our responsibilities. And we're seeing this assault now on climate science, based entirely on deception and manipulation, trying to put out into the public arena views of the world which will promulgate uncertainty and delay and confusion in the public mind. Very successful in this country. Now let's move on to the aspect of what should we be doing with the system. There's a classic paper by Dana Meadows some years ago, I think it was in the 90s, which had a bunch of how to intervene in complex systems, moving up through a list. And I'm not going to show you the whole list, but by the time you got to the bottom, it was basically that to really make a difference, you have to change your mindset. You have to change the way you think about the problem. And what I'm going to do here is just make a proposition that I'm sure many of you have heard in one form or another, that we simply, as humanity, start to base our planning and decisions for the Earth system based on Earth system reasoning, not on traditional economic arguments, that we must maximize growth, for example. And the reason for this is simple. It's likely we've already passed the carrying capacity of this planet, both in terms of population and in terms of what we regard as our consumption, our needs. And that's only the rich part of the world. There are billions of people on this planet who are still getting a very poor deal. And this, broadly, the rules I am proposing, the rules is kind of tongue-in-cheek, is that we have reached the point of impact on this planet that we must minimize impacts. And minimize impacts are several-fold. One is we must minimize the lifetime of all the human waste products in the Earth system and eliminate waste that has critical interactions with the biosphere. We must minimize the use of non-renewable raw materials, which essentially means maximizing recycling and essentially moving to an economy where we remanufacture everything. And we must maximize the efficiency with which society uses energy and water. And in order to do that, in order to power our society, we then have to maximize the use of renewable energy resources. Now, I can't possibly talk about all these things in half an hour or so. I'm going to talk a little bit about lifetime, and I'm going to talk a little bit about water, and then I'm going to talk about climate through the seasons. This is a schematic, the kind of things weather people draw, and it goes from the North Pole to the equator here. And it's a schematic of all the circulations. This is the polar regions, this is a mid-latitude front, and the tropics are over here, and there's a convergence zone in the tropics. And I just put it up there to explain that in the atmosphere, many different places in the atmosphere, the time scales are very different. Air flows from top to bottom, mixes up through the tropics in time scales of order days. In mid-latitudes where there's frontal systems and you see weather patterns grow and track across the United States, the time scales are more like a week. The exchange between the northern and southern hemispheres is months or longer. The exchanges between the troposphere, which is up to where the stratosphere begins and the temperature stops decreasing with height, is much longer, order of years, and occurs in specific places in the atmosphere where there's interaction. And the lifetime of things up in the stratosphere is much longer. Well, so if you're making something, you know, you're a chemical engineer, right now we make something and we dream up what it'd be good for, what it can be marketed for, how we can sell it, how we can create a need for it if it doesn't exist, and so on. But the questions we should be asking from the Earth's point of view is where will it be transported, and what is its decay and transformation path, and what is its impact on the climate and the biosphere. And basically, if you don't know the answers to those, don't make it, or delay. And the time scale for delay for the Earth system is something like 50 years or more. Now, you understand that's heresy from the point of view of economic growth to building delays of that. But that's one of the big challenges we face. I'll just give you some examples that you're probably familiar with. The chlorofluorocarbons, the CFCs, and what was replacing them, the HCFCs. Long history here. Back in the 30s, we made the first Freon refrigerants. That was their trade name. It meant the spread of refrigerators, the spread of air conditioning throughout society. We didn't find the breakdown. They were very stable, they were wonderful, they were non-flammable, non-toxic, tremendous technical triumph, and it gave us the ability to cool everywhere. They were used as propellants for bug sprays, hair conditioners, and things like that, up through the 50s and 60s and 70s. We didn't find what happened to them. We knew they were non-toxic and very, very stable until 74. When we found the breakdown pathways, theoretically. And then in 85, we discovered, big surprise, the Antarctic ozone hole, because these gases, and this is just a growth path here of one of them, Freon 11, was growing very steadily through the 70s and 80s until we introduced this so-called Montreal Protocol, and then it leveled out. The breakdown path was something very stable, something very inert. Nothing in the troposphere damaged it. Rose into the stratosphere. Lifetime of centuries. But eventually, sunlight starts to break down and split off the chlorine and fluorine atoms. The chlorine then interacted with ozone on ice over the southern pole and created the Antarctic ozone hole. Why is that a problem? Well, ozone, unfortunately, is the gas that protects us from the ultraviolet radiation from the sun. And just putting these gases and similar ones with bromine into the atmosphere has reduced the protective ozone layer. And it's going to take us the rest of the century with a whole series of transformations to try and get it down again. We've reduced the growth of the problem now. We haven't eliminated it. Well, we then replaced them with the HCFCs, which had an extra hydrogen atom on. The hydrogen meant that they only lasted for decades. They were more reactive in the stratosphere, not centuries. But unfortunately, the HCFCs are very powerful greenhouse gases. So putting them from all our refrigeration into the atmosphere is producing another problem, accelerating the warming of the planet, and we're now trying to phase them out by 2020 and replace them with something else. Now, the underlying message here is a bit of a problem for us psychologically, because basically, except for our inputs, the climate system is not under our control. And we live in a world where we'd love to control everything. And we expect to be able to control our personal environment. Of course, the engineers dream up ways of geoengineering, putting shades up in space. But basically, they're essentially dreams, except for possibly the direct removal of atmospheric CO2 by some technology. And it's worse than just that we can't control the system. At the moment, the imbalances in the planetary energy balance are rather small, just 1 or 2 watts per meter squared. But there are lots of changes that result from that because of positive feedbacks in the climate system. And we know that on many timescales, including the long timescales of the ice ages, the climate system's rather unstable. So we're perturbing it, but because it's rather unstable, we are not that certain of where it will go. And it's very big. There's large response lags in the system, and that means that what we do in our human society, we don't see the impact for 50 or 100 years. And that's a problem for us. One generation doesn't see the impact. And the sad news for your generation is that our generation, which has seen the impact, has basically done nothing about it. And you and the next generation will have to deal with it. Technical slide. The greenhouse gases, very simple in sense. Oh, didn't mean that one. The atmosphere is transparent to the light, solar energy from the sun, but not at all transparent to the heat or infrared energy from the Earth, because all these molecules, not oxygen and nitrogen, the more complex ones, they vibrate, they absorb energy from the Earth. So the Earth tries to cool to space, and essentially everything is absorbed in the atmosphere, radiated back down, and radiated to space from higher levels. Critical, absolutely critical process. If it wasn't for those greenhouse gases in the atmosphere, which keep the Earth something like 59 Fahrenheit warmer, the oceans will be frozen, be a problem. But what we are doing now is we are increasing one of the greenhouse gases, and this one to a lesser extent. This is coupled to the temperature, and of course we're putting in a bunch of others as well. And we expect that the temperature of this planet, if we stay on our present emission path, will go up substantially this century. Maybe only about 10% on the greenhouse effect that we have as a natural system, but enough to transform our planet. Floating sea ice. I'm going to say a couple of bits about the system. I'm going to say a little bit about floating sea ice, because ice is a very important indicator on this planet of what's happening. The floating sea ice is a rather fast response. Think timescales, years. And what we've seen over the last 50 years is a thinning of the northern ice cap of floating sea ice. We first noticed it from submarines. Over about 30 years, it got about 40% thinner. And they were just measuring the thickness because the submarines, of course, wanted to be able to come up to the surface. So it was a critical measurement for them. And this has a couple of impacts. One is that ice reflects a lot of sunlight. And the sun is above the horizon in the summer in the Arctic. The reduced reflection, which we call the albedo, increases the polar warming, because if sun melts, there's less reflection, more energy reaches the surface. But when the water is opened, instead of ice covering it, there's then more evaporation from the ocean surface, and the evaporation goes up and increases the water vapor, which is a powerful greenhouse gas. And then a lot of subsidiary things happen. When the water is open, you get more storms and more mixing. It blows the ice and also makes life more miserable for the Inuit and other native peoples up there. Doesn't affect sea level, however, hardly at all. It affects the energetics of the planet a lot. And what we've seen in the last 5 years is an accelerated melt of the sea ice. The big loss year was in 2007, and about 40% of the ice cap melted. A lot of it just got blown out of here. The winds were favorable that year, and it got very thin. It's come back a little bit the last couple of years. This was a schematic of the minimum of ice at the end of the melt season in September. Watch it this year, because although 2009 was not as low as 2007, they've pretty well tracked through the winter. That is, we're not getting back to the ice cover that we used to have in winter. And the ice now is mostly only a year or so old. Now, the grounded ice sheets are a very different story for the Earth. They have very long time scales, decades out to centuries, 1,000 years or so. And what they're doing now is melting, but they're only melting very slowly, and they're soaking up a little bit of the energy imbalance of the Earth. So there's more energy coming in than can escape through the greenhouse atmosphere. A little bit of that is being soaked up by melting ice. But we can see that because as the ice melts, sea level rise is accelerating. It's only coming up a little bit. The ice melt is only contributing a couple of millimeters a year, and there's another one from the expansion of the oceans as they get warmer. But even this is something which is coupled to other things. Dirt, soot, aerosols, pollution that lands on those ice sheets increases their absorption, reduces their reflection, increases the melt. And another thing that happens is the oceans go up under the glaciers and melt them from beneath. We know from the past that sea level has come up as much as a couple of meters per century for long time periods as large ice sheets have collapsed. And it looks as if we're heading in the same direction, with Greenland likely to be the first old ice sheet to melt. Lots of very active research there because, I'll show you a couple of pictures. This is just one of these pictures of how much. This is the melt area in 2005. That's how much was melting in 92. And there were, I haven't been able to get a nice picture, but 2007 was more. And what's going on there is a kind of a fantasy when you try to come and research it. These people are standing maybe 5,000 feet up on the top of a mile of ice and watching it melt and flow down through these crevasses, they're called moulins, to the base of the ice sheet, where they slosh around the bottom and they maybe help lubricate it and help the glaciers slip into the sea. It's a very complex process. People are trying to track that water through the ice sheets. We have gravity satellites measuring every year how much ice is lost, and we can follow year by year the acceleration of the process, way beyond our control, except what we put into the atmosphere. And most of you probably aren't aware that because of those massive ice sheets, the base of many of the ice sheets are actually below sea level. So water can come up the fronts of the glaciers underneath seawater, which is above freezing, and melt from beneath. A slide for that. This is one in Greenland. You realize that seawater is actually undercutting this and helping the melt. Now, coming from my field, my philosophy is, well, wouldn't it be nice if we could actually understand all this? Wouldn't it be nice if the public understood all this? Because the public would then see the significance of what we were doing and would start, when they read something, that, oh, this is all some fantasy. By the way, what's called full disclosure, I'm part of the climate conspiracy that some of you must have read about, according to John McClory in the newspaper. Because I've been talking about this for years, so I must be part of the conspiracy. The water cycle is central to climate. It's central to life on this planet. It's central to us. There's not a problem here in Vermont, but there are many places where we actually have water shortages. We can always model the future, but the difficulty here is understanding what is real. So I'm going to try and talk a little bit about the coupling of water, life, and all the climate processes from just the seasonal cycle that you all know and are familiar with, at least if you've lived in Vermont for at least 1 year. This one came before that. This is just the kind of thing we do of modeling the future. This is the annual winter and summer change in temperature, the end of the century, just for North America. The degrees are centigrade, so this is 4 degrees warming centigrade in winter, in summer, from a bunch of models averaged if we stay on our present path. And this is water, drier in the subtropics, much wetter in the high latitudes. But let's try and understand some of the things that are going on in terms of things you can understand. This is something to look out for the next month. Okay, you look at that and you probably just see daffodils on a sunny day. It's actually the 15th of April, 2008. And with that year, we had 10 days or so of lovely, warm, sunny days like this, with the temperature at least well up into the 70s. And it doesn't happen every year. We're having a little bit of it the next few days a month earlier, not such high temperatures, just in the 50s. The way to think about this, though, is it's a critical example of something that's happening in the climate system. In early spring, we're past the equinox, the sun is going up in the sky. Okay? It's getting warmer and warmer. That heats the Earth's surface. First thing it does is melt the snow and melt the frost in the ground. The frost is already gone. I'm already digging over my garden and planting in Pittsford. But apart from a few things like the daffodils, which are just only half that size at the moment, there's no real evaporation from the surface. Okay, it rained a day or two ago, and there's an evaporation for a day. The plants, the trees are not yet in leaf. There's not the big evaporation that comes in spring. Without the evaporation, all the heat goes into heating the ground and comes back to the atmosphere as just heat. That can give us quite warm temperatures up until leaf out. And what happens with leaf out, so it warms up the earth rapidly. That tells all the biological processes, spring is here, let's start. But it remains warm and dry with very little water vapor in the atmosphere, blue skies, little cloud, means no greenhouse effect until leaf out occurs, which here doesn't occur till around the 1st of May. With climate change, spring is coming a few days earlier, maybe a week earlier than 30 years ago when I started gardening in Vermont. There's one other big transition there that you are aware of but may not have thought about, is the relationship between the greenhouse effect, that's water vapor and clouds in the atmosphere which trap the Earth's heat, and the frosts. As long as we have this condition in April, frosts are frequent. Like the next few days, it may get up into the 50s, but there'll be a frost at night, at least the next 2 days. Until that evaporation turns on, produces more water vapor and clouds in the atmosphere, frosts continue. Vegetation comes to life. The frosts basically shut down for the whole growth season. We'll come back to that at the other end of the season. Same thing in words. There's a lot of seasonal lags, melting of the frozen soils. There's a coupling between the vegetation and evaporation. It's the latent heat of evaporation, as we call it, that reduces the surface temperature. And there's a lot of interesting coupling: evaporation, humidity, clouds, water vapor, greenhouse, and the diurnal temperature range through the long-wave net cooling of the Earth to space. In the summer, most of what goes on deals with the coupling between how much water there is in the ground and evaporation to the planet. And that's a positive feedback. If the ground is very wet, you can get a lot of evaporation, a lot more clouds, and more rain. If it's very dry, you can get the opposite. That you can get lock in a dry spell or a drought. And if you remember back to last year, was a classic example of a wet summer. We had tremendous amount of rainfall. You could just see the water evaporating off the trees and the clouds in the valleys at sunrise. This is floods on the Otter Creek. We had 2 very wet summers with direct fast evaporation of the canopies, giving us this positive evaporation precipitation feedback. It just locked in for the summer and the fall last year. Of course, the farmers want the opposite. They want it to be wet in spring and then have a dry down so they can have fun with their hay. Well, haying can be fun, but it's hard work. Now in the fall, it's like the mirror opposite, in which vegetation is basically trying to postpone that first killing frost. As we come, the transition in the fall happens later than the one in spring. We're well past the equinox by October 1, which is when we first get our first frost. The sun is already sinking rapidly, but typically through September, the deciduous trees are still evaporating. There's still lots of water vapor, there's a lot of greenhouse effect. That reduces the cooling to space, it reduces the drop of temperature at night, and it basically prevents us having a frost. So as long as those trees can keep evaporating, they can delay the first frost, which will kill them, or tell them to shut down for the winter, until one night, things that are not under their control, some air blows down from Canada where everything has died already, and it kills them, gives a frost. Then the frosts become frequent. So typically with that first frost is a signal to the trees, and it's also the transition between no frosts and lots of frosts. And then we get warm nights again, warm days and cool nights, what we think of as an Indian summer, kind of the opposite of the spring, but not as strong because it's always much later in the year relative to the equinox by early October. Our beautiful trees are linked up to that. The trees, if they get a frost early, then we get more color from them typically. And these have had a frost, and notice the sky is blue. That's a low greenhouse effect sky as far as low water vapor. I'm not talking about the CO2 part of the problem, just the water vapor that's coupled to climate. Now in winter, the thing to think about winter, and I know you're just trying desperately to forget it unless you're skiers, is that but it was very, very vivid this year. The first heavy snow begins as a plunge of temperature. And it does it through two processes again. One is the reflection of sunlight. The net radiation balance, as we call it, of the Earth basically drops to zero with that first clear snowfall, which has a very high reflection. But also the dumping of the snow on the ground, the evaporation of snow and ice is much less than the evaporation of water. And that reduces the water vapor and the water vapor greenhouse and speeds up the cooling of the air to space. Now, in the climate system, that same thing that happens, it happened with the first snowfall in December this last winter, is similar to what we see at the North Pole in the polar regions for the climate system. And it's related also to the accelerated warming and melting in the Arctic. We'll skip over that. I'll skip over the technical details there, and I'll skip over the energetics. In graphical terms, here's a couple of shots of the same scene, one cold winter and one warm winter. Here I'm just looking across my garden at the floodplain of the Otter Creek, and you can see several important things. One is, notice that the forested mountains are still dark, but the hay fields that are covered with snow are very bright. They're reflecting a lot of sun. The forests are not. And the forests don't because they shadow the snow. They shade the snow so the sun never reaches the snow when it's at a low angle. And that is the very, very important difference between what forests and grassland do to the climate system. But it's also relevant to what's happening in the Arctic. Shrubs are growing up in the warmer Arctic through the snow, and that effectively makes the snow darker. They're little trees. And that's something that then will accelerate the warming. And that's happening across Alaska at the moment in many areas. Clear sky, very little cloud. This is another year where the grass was still green. I was still digging my garden. There was floods everywhere. This whole landscape is absorbing most of the sunshine. Well, I'm going to wrap up in just a few moments, so let's come back to the big picture issues. We don't know when we pass the carrying capacity of this planet at a reasonable standard of living, but we've probably already passed it. And population is still rising, consumption is still rising, fossil fuel use is still rising. And I've just put on one of the, I don't know which of the international agencies is responsible for this, projections of future population on this planet. And you can, this is 1 billion, this is 10 billion, and we're here around 2010, around 6.7 or so billion people. And this is an attempt to project population of this planet out for the rest of this century. And it's like all these graphs, you can see no one has any idea how to do it. They have a high estimate, a middle estimate, and a low estimate. The high estimate is the kind of fantasy that somehow we will solve all our food problems, our resource problems, our environmental problems, and we'll be able to feed a steadily growing population and double the population again by the end of the century. And the other one, the low estimate, is either we will succeed in, by choice, limiting our population and going into a declining population somewhere which the Earth could support, or catastrophes will do it for us. But this is like an energy projection chart. You don't know what the future is going to bring, but it highlights for us the fundamental issue that if we want to have a population on this planet that we can, where we don't have massive poverty, massive starvation, and everybody has a reasonable standard of life, we're going to have to figure out a way to make the transition. And the transition means having less than the replacement population per family out for the next 100 years, roughly. Oh, I forgot to say, we still believe in growth. We believe in growth, right? We're desperately trying to get back to a growth cycle, and what's growing, of course, is global poverty and suffering. Similar kinds of graphs, this one actually comes from Stern, for what kind of transition for energy for the future. This is business as usual, with billions of tons of CO2 emissions globally for the planet, and that essentially will push us back to, we've got the fossil fuel to do that, mostly in coal reserves. We can push the atmospheric CO2 on this planet up to levels it hasn't had for 20 million years and melt the ice caps. We can do it. It'll take centuries, but we can do it. And we will learn by that because it will flood our coastal cities and we'll shut down eventually. But the various proposals that have been made that were debated heavily there in the Copenhagen meeting in December, this is the one, what we would have to do to stabilize Earth's CO2 at 550 parts per million equivalent, this to drop it to 450. And if you, those of you who are following the Copenhagen discussions, about 70 countries said we should be shooting for a target of 350 parts per million, and we're already up to 387 or 8. And we're here. You see basically where all these paths diverge, the future. And 350 isn't on here, but it's really not only do we make the transition next year, but we come down very, very steeply. This is reducing our fossil emissions as a global planet. So you can see huge issues here that we have not yet, we're still trying to get back onto that path and get away from the recession, which did wonders for the planet. It actually dropped this by a few percent in 2008-9. So back to my guidelines as I start to wrap up here. Given that this planet is basically not under our control, we can understand a lot of it. We can make some intelligent choices and decisions. A strategy with the population and consumption and energy use we have is we have to minimize and maximize a lot of things that represent, we have to minimize the human impacts on the system, minimize lifetime of our waste products, minimize the use of non-renewable things, maximize the efficiency with which we use energy and water, and make the shift to renewable resources. Well, if my talk is any good, that seems rather simple, right? I'm glad somebody has a sense of humor. It isn't simple. In principle, it's simple. All we have to do is replace our infrastructure. Replacing cars is maybe 10 years. Replacing, we know how to build efficient cars. Replacing power plants tends to take longer, like 30 or 40 years. Replacing or retrofitting our housing is also decadal timescales. In principle, we know what to do most of those things. But of course, in practice, nobody wants to do it. Why? Well, it would affect our standard of living. Oh, our standard of living. Which basically boils down to our right to drive Hummers or something like that. At a more subtle level, it would require that we manage things. Managing the Earth system is a huge task. And politically, management is a bad word, and we know why. Most of our government systems manage rather badly. It means management on the local scale, as we would have to manage our own lives more efficiently, and we'd have to manage our communities and move up to the global scale. There are all these deeply held value systems we have about our rights and our freedoms, and the fact that all our economics is based on this wonderful word called growth. Well, there's nothing in the natural system that has unlimited growth, and those that do have our ecosystems have unlimited growth and then population collapse. There's a lot of belief that somehow technology will come along and save us. After all, it did produce this problem. And we'll just continue as we go until somehow those miracles are achieved. And you technologists here, it's your job to fix the Earth. So at the moment, we're in a situation where most political systems will pay some kind of lip service, but they won't actually do anything. To make it more explicit, let's cast it in US North American language. And I've cast this as the ways in which we deceive ourselves. And I've said the 3 pillars of the American dream are crumbling. And I'm sure you don't want to hear this, so you can close your eyes and go to sleep. One is this, what I've talked about already, economic growth, which has basically been built energetically on fossil fuels, financially on debt, and the market driving consumerism is unsustainable. And I suspect many of you realize that. But from my perspective, it's a disaster for the planet. Now we're coming back to our rights, and the individual rights and the needs of humanity have to be balanced in some way with the needs of the Earth system. At our level in the United States, we have a constitution. It doesn't give any rights to the Earth, but it gives lots of rights to us. And if somebody tramples on my rights, you know what I have to do about it. And technology is a problem in itself because we have gone down this technological growth path without thinking about it. without thinking about how we really manage technology. Every now and then we come up with something. The manipulation of the human genome is an example where we have to think about how far we're going to go down that path, and different countries have taken different routes. But the result is we have tremendous successes, and most of you could probably would view technology as a tremendous success. But we also have catastrophic failures, and the Earth system is heading for catastrophic failure at the moment. And nuclear power is another example of catastrophic failure that I won't discuss at the moment, because mostly it's links to nuclear weapons. So what do we need? Well, we've got to find some more honest and truthful and very smart pathway forward. And this is difficult. I give lots of talks around the state, and I'm talking to 4th graders or 3rd graders. The teacher always said to me, please don't frighten my children. And that's, well, of course, for kindergarten and 1st grade, I show them pretty pictures, and I don't frighten anybody. But most of our society is being manipulated by fear. And fear on this issue, if all I have done is make you think, oh, this is a huge problem, I can't solve it, I better go back to, my escape routes, whatever those are, you become paralyzed. We have to think and frame things in ways that will spread hope and not anger. There's an awful lot of anger in our society at the moment over people realizing on some level they have not got what they dreamed of. And they certainly don't like to be told they really need to change direction. But we do need to change direction, and we need to do it at a community level. And we need to find language that will sidestep all the ideological barriers that there are in this community. Because most of our political language in particular is so rooted in the past and irrelevant to dealing with the Earth system. People have talked about adaptive governance. Well, that's a very different system from constitutional governments. And we have to be able to adapt on the fly when we understand more about the system. And fundamentally, we need something that respects both Earth system processes and Earth system limits. Well, I don't need to tell you probably that we don't like limits. And that's where I was going to pause for discussion. I have a few copies, not enough for all of you, here of my slides for those of you who want to think about it further, or you can always email me for details.